Okay, now that we've talked about the sampling distribution of sample means, we're going to talk about the normal condition. So if our original population distribution is normal, our sampling distribution will also be normal. But what if our original population distribution is not normal? In fact, most population distributions are not normal. So what we have here is a really strange population distribution from Rice University. And so that's the original population distribution. And so now what we're going to do is we're going to look at what happens to the sampling distribution as our sample size gets larger. So here we have a sample size of 2, and this is our sampling distribution. So it kind of brings it together more. And here we have a sample size of 5. Brings it together even more. A little bit more symmetrical, not quite bell-shaped, but more symmetrical. And here we have a sampling size of 10. And look how it pulls together more, closer and closer to normal. And then here we have a sampling size of 25. Almost a true bell-shaped curve. And so as that sample size gets larger and larger, it doesn't matter how the original distribution looked. It comes closer and closer to normal. And so again, more symmetric and more normal as that sample size increases. So what does this mean? This means that as long as our sample is large enough, the distribution of the sample means is very close to normal, no matter the shape of the original population. So how are we going to use this every day? Well, we're going to use what we call the central limit theorem. And that says that if we're doing a sampling distribution of size n from any population, then the central limit theorem says that when a sample size is normal, the sampling distribution will also be normal. Wait, those are switched around. Hold on. Okay, when the sample size is large, and we're looking at large being greater than 30. So we want our sample size to be bigger than 30 if the population distribution is not already normal. Then our sampling distribution will be normal. So now our normal condition for means is that n has to be large. It just has to be greater than 30. So for proportions, we have a condition that of this. And so this is for the p hat, but for our x bar, so this is for proportions, and this is for means. Those are our normal conditions, and that allows us to use the normal CDFs. Now keep in mind, this is if it's not already normal. If it's already normal, it doesn't matter our sample size. But if we know that the original distribution is not normal, we use this normal condition and is greater than or equal to 30. So how's that going to look in a sample problem? Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that students at your school are typical texters, how likely is it that a random sample of 50 students will have sent more than a total of 1,000 texts in 24 hours or in a day? So does it meet the normal condition? Yes. How do I know it meets the normal condition? Because n is 50 and 50 is greater than or equal to 30. So it doesn't matter because it's bigger than 30 what the original shape was. It doesn't matter that it was right skewed to begin with, because my sample size is big enough that the sampling distribution becomes approximately normal. So now what is the mean of the sampling distribution? The mean of our sampling distribution should be the same as the mean of the population distribution, which is 15. Now the standard deviation of the sampling distribution should be 35 divided by the square root of my sample size. Which is 4.94974746.8. Again, using as many decimal places as possible to minimize that error. So what is the probability that a simple random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? Well, now that we know it's approximately normal, we can use a normal CDF. The lower bound is 1,000. Upper bound needs to be something really, really big. So let's say 10,000. We already know our mean is 15. And our standard deviation is 4.9497, blah, 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 blah. Now, I'm thinking there's something wrong because those numbers seem really big for that mean. So I'm going to reread my problem and see if I read something wrong or if I wasn't. Okay, so there is something wrong because we're looking at 50 students altogether sending a total of 1,000 tasks. So when we're looking at this lower bound and upper bound, we want to know how much per student. So how much per student would be 1,000 divided by 50. That makes it way more reasonable to assume. So we're looking at 20 here. There we go, that looks much better. And so then our upper bound is going to be something ridiculously high. So our upper bound will be 100. That makes way more sense. See what happens when I rush through things and don't totally think about them. So lower bound of 20, upper bound of 100, mean of 15, standard deviation of, I'm going to go ahead and just type 35 divided by the square root of 50. And we get 0.1562. So about a 15% chance. Okay, and so that's it for chapter 7 so far. We're going to keep building on these ideas, so these normal conditions will keep following through over and over and over.